Today, I'll talk about some of my recent work in which I've been looking at the impact of regional scale mantle structure beneath the West Antarctic Rift System on glacial isostatic adjustment, or GIA. This is a map of ice mass change from 2003 to 2019 across Antarctica. And looking at this, so the reds are areas with more ice mass loss, whereas blue is ice mass gain, actually. So a lot of the ice mass loss has been really focused in West Antarctica and more particularly in the Amundsen Sea embayment region. And in this region, we also have the West Antarctic Rift System sits in across West Antarctica, which underwent its major extensional phase in the late Cretaceous. And then there's some evidence for localized Cenozoic extension. So this is a map of upper mantle viscosity at 120 kilometers depth. So we're observing really rapid uplift in response to ice mass loss in the Amundsen Sea embayment, and this is likely due to this, or it's due to this low viscosity upper mantle material. So we know that there are, I'm trying to switch slides, but okay. We know that there's a range of interactions that occur between the solid Earth and the cryosphere that can act to either stabilize or destabilize the ice sheet. So this is just a diagram with some of these interactions. But a lot of my work is really focused on better understanding glacial isostatic adjustment. So the solid Earth response to changes in the distribution of ice and water at Earth's surface. And the glacial isostatic adjustment really are, and the pattern of magnitude of the solid Earth response to ice mass loss is really strongly dependent on solid Earth structure. So it depends on the thickness of the lithosphere and the viscosity of the upper mantle. So in a region where we have thinner lithosphere and a warmer, generally lower viscosity upper mantle material, we're going to get a much more rapid uplift rate. So a glacial isostatic adjustment response time on the order of 10 to 100 years. Whereas in an area where we have maybe a thicker lithosphere, a cooler upper mantle material, corresponding to higher viscosity upper mantle, we're going to get a much slower GIA response time. And in West Antarctica and in the Amundsen Sea embayment region, we know that we have something more like this situation on the left. So we have this warmer, low viscosity upper mantle, a thinner lithosphere. So this is why we're getting these we're observing these rapid uplift rates. So we know that solid Earth structure has a major impact on glacial isostatic adjustment. So really, in order to better characterize interactions between the solid Earth and the ice sheet, it's quite critical to place high resolution constraints on solid Earth structure. So over the past 20 years or so, there's been a real surge in seismic station deployments across, so these are broadband seismic stations across Antarctica. And a lot of my work imaging upper mantle structure has really been focused in West Antarctica. So I've been using, mostly using data collected on the Polar Earth Observing Network seismic stations, so the POLNet stations, which are shown in blue here. So just for, I guess, a bit of context on what these stations look like, we just deploy these seismic stations directly onto the snow or ice, and then they'll get buried. And unlike other seismic stations around the world that the data is just telemetered back to some sort of central data center, if we don't actually go and pick up the data from these stations, we never get that data. So it's pretty critical that we actually go to these sites and pick up the data, or we won't have the means to better constrain solid Earth structure. So prior to the collection of this seismic data and the subsequent seismic imaging that followed, it was long debated how much of the present day rift morphology in West Antarctica resulted from late Cretaceous extension of the West Antarctic Rift System versus Cenozoic to recent extension. So here I'm showing a bedrock topography map of central West Antarctica, this area here. I labeled the West Antarctic Rift System, and there's 4 major crustal blocks in West Antarctica that are outlined in red. And as you can see, there's some deep subglacial basins in the West Antarctic Rift System. I'm marking the seismic stations with triangles here. And then I label the Thwaites Glacier and the Pine Island Glacier, which are two of the glaciers that are losing the most mass of any glaciers in Antarctica. So, and so basically, we before our seismic imaging, it was unclear how much extension happened 100 to 83 million years ago versus 46 million years ago. And with the regional seismic imaging and continental scale seismic imaging, we've been able to better understand heterogeneity in upper mantle structure throughout this region and try to use that to better understand the tectonic history of the region. So for my work, we found that there are these high velocity anomalies throughout much of the rift system. So the rift system sits here, and then again, these crustal blocks outlined in red. So the rift systems here, we have pretty high viscosity or velocities across the rift system. And this is really indicative of cooler lithosphere, unmodified by tectonic activity since the late Cretaceous extension. But there is a lot of low velocity anomalies throughout the region. So in Marie Birdland, this crustal block, we have a lot of Cenozoic volcanism. And so hence why we are seeing these lower velocity anomalies. And then there's some evidence that there's some sort of mantle flow from Marie Birdland across the mouth of the Thwaites Glacier and beneath the Pine Island Glacier. But there's also low velocity anomalies that we see elsewhere in West Antarctica. So these are suggestive of more local or focused Cenozoic extension. So we know that portions of West Antarctica are underlain by particularly low viscosity upper mantle. But the question is, what is the length scale over which laterally varying mantle structure actually impacts the solid Earth response to ice mass flux? So previous glacial isostatic adjustment studies have really incorporated solid Earth structure variability inferred from continental scale seismic imaging. So this is an example of a continental scale imaging of the entire Antarctic continent from Lloyd et al. 2020. And here they're really only capturing variability at 200-kilometer length scales. However, for my work, there is evidence for strong variability over 50 to 100-kilometer length scales. So, so currently I'm working on investigating how this actually impacts GIA using the CCON. It's a global 3D glacial isostatic adjustment model that computes solid Earth deformation and global sea level changes in response to a given ice loading change. So for my current work, I'm using ice loading changes for the modern, so over the past 120 years or so, and then projected ice mass changes in the region, or actually across the continent out to 2300. And I've constructed various solid Earth models that infer upper mantle viscosity variability from continental seismic imaging and regional seismic imaging. So as you can see, we capture a lot more short wavelength variability in upper mantle viscosity with the regional models of Earth structure compared to the continental models. So we have like a stronger transition from lower viscosities at this grounding line region, which is where ice goes from sitting on bedrock to floating on the ocean. So we have a stronger transition from lower viscosities at the grounding line to higher viscosities in the interior in these regional models. And then this model outputs predictions of surface deformation, sea level change, and geoid change. So, okay, so I'm finding that regional structure does have pretty significant impact on GIA predictions for modern ice changes over the past 125 years. So here is the modern ice model. Again, Thwaites Glacier sits here. So this is the Amundsen Sea embayment region in this area. Pine Island Glacier is here. And as you can see, a lot of the ice mass loss is focused at Thwaites Pine Island, and in this region, the Pope Smith Kohler Glaciers region. And then here I'm showing model predictions, the difference in model predictions using the regional versus the continental scale Earth models. So this is the difference in GI predictions for relative sea level change. So there's up to 19 centimeters difference in sea level change predictions with the incorporation of this regional scale Earth structure. And then there's also predictions of crustal motion. So here I'm plotting GPS stations deployed on bedrock throughout the region with these squares. So it's important to better understand what are GIA models, crustal motion predictions from these models. So here's between the two model, or the regional and the continental scale Earth models, we are finding 15 to 20% difference in vertical crustal motion predictions and up to 5 millimeters per year difference in horizontal crustal motion predictions. And so we've been comparing, so there's GPS stations deployed on bedrock throughout the region. So this isn't measuring the change in ice. These stations aren't measuring the change in ice surface height, but actually in solid earth deformation. So we've been comparing our model predictions with observed crustal motions. And so here's horizontal crustal motions. The observed are plotted in black, and then horizontal crustal motion predictions from our various Earth models are shown in the different colors. And and then here I'm showing the magnitude of vertical crustal motion rates for simulations with the various Earth models in different colors, and then the observed vertical crustal motion rates in black, and again for our horizontal crustal motion rates. So in general, the model predictions are inconsistent with observed crustal motion, and this is a common problem in GIA modeling at the moment. Basically, no glacial isostatic adjustment models can produce the observed crustal motions. And this is likely or can be attributed to issues with Earth structure, so the Earth model or the ice model that we use in these glacial isostatic adjustment models. So we really need to continue to work to improve both. But it's particularly difficult to constrain ice mass changes prior to the satellite observing era, because there's not that many, we just can't do it that well at the moment.
Okay, that's about 10 minutes.
Yep. Okay. So, and then now looking at future implication or future glacial isostatic adjustment predictions, we're finding that really constraining this viscosity transition that I mentioned earlier at the grounding line of in West Antarctica and at the Thwaites Glacier and Pine Island Glacier in particular is going to be critical for improving glacial isostatic adjustment predictions. So you see the biggest differences in the regional versus continental simulations at the grounding line at, so this is 2050, 2150, and 2300. But as soon as 2300, we're seeing that upper mantle features located 500 kilometers inland of the modern grounding line start impacting our sea level change predictions. So this is this feature that I label C here, which is associated, it's in the seismic velocity models, it's a localized low velocity anomaly. So here it shows up as a low viscosity anomaly associated with the localized Cenozoic extension. So these features inland within the rift system really start impacting our sea level change predictions relatively soon. And from this work, we're also finding that really accounting for regional variability in Earth structure is going to be necessary to accurately predict future bedrock elevation changes. So these are bed elevation profiles across the Thwaites Glacier, so here, and then the Pine Island Glacier, and then differences in or bed elevation change predictions from various Earth models, so including this continental and regional scale structure. And here the grounding line is shown as a dotted line. So, and again, the grounding line is where the ice goes from sitting on the bedrock to floating on the ocean. And this improving constraints on bed elevation change at this interface is really critical for improving projections of future ice mass changes and projected sea level rise, because if you have higher elevation at bedrock at the grounding line, you're going to have lower sea level, and you're going to get less ice mass flux across this interface. So you'll have less ice mass loss in general across the ice sheet. And we're finding up to, with the incorporation of regional scale or structure, up to 30-meter difference at Thwaites Glacier at the grounding line. So it'll be important to consider higher resolution or structure in the future. So here, I'll just summarize by basically what I just said, which is if you have this rapid glacial isostatic adjustment, you can actually raise the elevation of the grounding line, lower local sea level, and then you'll have reduced ice flux. So from this, we know that constraining solid earth ice sheet feedback processes will really be critical for reducing uncertainties in estimates of projected sea level change from Antarctica. And considering solid earth structure, which is in West Antarctica, really intrinsically related to the tectonic evolution of the West Antarctic Rift System, will be especially critical for better constraining these future ice mass changes and sea level rise projections. And yeah, with that, I'll take questions.
Thanks very much. Brilliant. So any questions from the audience?
I completely lost the Zoom.
Kim, you had a question?
Yeah, thanks, Erica. That was a great talk. I have a question about one of the first slides you were showing the low viscosity asthenosphere plot from, I think, Gomez, and it was really bimodal between the east and the west.
Right.
Is that being constrained by passive seismic, just like your stuff, and it's just a question of resolution, or is there an extra data source that's feeding that model of low viscosity asthenosphere?
That's from the seismic, but we know like East Antarctica has undergone much less, a lot less tectonic activity recently than West Antarctica. So it's to be expected from like the geologic setting too, that we have much higher viscosities in East Antarctica than West. So,
okay. But basically both your study and the earlier study are seismically based. It's kind of improving resolution over time, effectively. And
right. Yeah. Okay. And if we, we still have pretty sparse seismic station coverage in West Antarctica. So like, and in East Antarctica too. So, maybe it wouldn't be, if we could do more regional scale imaging in both areas, then with denser seismic networks, we'd be able to constrain more variability, but we can't at the moment.
Thank you.
Yeah.
Thanks. So I have a question about the GPS velocities. What was the one plot showed some horizontal motions? What causes those?
What causes them? Well,
what's the explanation? Is it just the same process as the? Yeah.
Yes. So you'll have like when you, basically those are related to like lateral variability in the earth structure. But when you load landmass, you're also going to have like the bulges, like the peripheral bulge formation, and then those will collapse as you start melting the ice. So this will all contribute to horizontal crustal motions. But I guess with respect to horizontal crustal motions, they're even more sensitive to these lateral variations in earth structure. So if we don't have really accurate constraints on the lateral variability, then it's really hard to produce these accurate horizontal crustal motions. But also like the pattern of ice mass changes is also huge for horizontal crustal motions. But yeah.
Is there any evidence for like current rifting in this rift, or is it impossible to constrain that because of all the complications to the GPS data from the glacial rebound?
There's not really super convincing evidence for current rifting from the GPS, from the horizontal crustal motions, because they could be explained by GIA. And there's not a lot of tectonic seismicity through the region, which you know, there's probably not current extension, but I don't think we can completely rule it out at the moment. So, yeah, possibly, but it's unclear.
Okay, thanks. Are there any questions from the audience? I've got one last question. If not, how high would Antarctica be if you melted all the ice? Like, what would happen to the continent? What would the final elevation be?
Well,
Yeah.
West, West Antarctica and East Antarctica would be very different because West Antarctica is marine basin, so it'd still be below sea level. Whereas East Antarctica is more of a plateau, so you just raise the plateau a bit more, but I don't know the exact numbers. It would be like spatially variable too. So, yeah, actually, West Antarctica would just become part of the ocean. A lot of it. There'd be some that would be above sea level, but